Let's start just by going through this synthesis that we were discussing previously. So again, the idea here is that we have a few different protecting groups. Not clear that necessarily we're going to need all three protecting groups, but the point is we may want to put something on one end and then put something on the other end in orthogonal nature such that we can begin to make these bonds. And again, in this case, what we discussed is the fact that you have free amine here as well that might be protected as something. And so, as we planned on last week, what we were going to do, you don't have to go this direction, but we decided that what we were going to do, I believe, was go from left to right. And so what we were going to start by, from a retrosynthetic standpoint, right, protecting group 1. Protecting group 1. Right, so this is effectively going to be our one target, and then what we're going to couple that to, right, is going to be an amine. Again, there's nothing wrong with doing and we can imagine something like this, right, where if we can get to compounds like this, once we form those bonds, if we really wanted to, again, I sort of gave one potential strategy where you could use all three, but if you start doing something like a retrosynthesis, what you notice is that, well, I want to do this coupling reaction, right? Here's protecting group 1. That can be acid sensitive, it could be base sensitive, or it could be hydrogenated sensitive. And again, if you decide to pick one at the end, you may decide to go with a protecting group from a strategy standpoint, where after you couple these, you can just do a global deprotection that would take care of them all. So again, that could be an option. If it's something different, you could just do 2 cycles. But the point is that sometimes you can strategize in this way. Okay? And then again, at that point, from a retrosynthesis standpoint, what you can, again, imagine is, well, now we need to make this bond, right? So we're going to have that amide bond, and what we also need is one. And again, since we're going to be doing this coupling, we're going to need some type of protecting group over here, and this is where we're going to need the orthogonality, right? So at this point, what I'll just say is protecting group 2. Okay? So again, the idea, at least as a quick retrosynthesis standpoint, is that, again, we don't have to go this way. This is just one option out of many, right? We're going to start with this dipeptide, which would be this one. Again, we want to protect the amines from a strategy standpoint. Then we're going to couple it to this compound. And if we look at it again, you don't need to do this. You could use the other one. But from an efficiency standpoint, one of the things you can imagine is using the same class of protecting groups, at least something that can come off at the very end, so that you can couple them, right? So you can couple and then deprotect, right? Now, again, here's the only time, in fact, so I sort of showed you guys the 3 protecting groups. In this case, you might not need 3 protecting groups, because you can clearly see that with an orthogonal protecting group here, right, if we simply did the coupling here and then removed it, then we would have the free acid. So again, it would be a couple followed by deprotect one here. right? And so this is just a sort of a quick general strategy, right? And then the question would become, how do you synthesize these groups, right? And so we discussed last week, I believe, right. What's that? So that could, on this side over here? No, right, on this one. Right, and so one of the things that you can do, right, is we can imagine that protecting group 2, if now what we want to do is actually think about real molecules, we could use the FMOC. Again, in terms of what FMOC is, just we have an FMOC protecting group here. And what we discussed was that we could put, say, for example, a butyl group here. We could put a benzyl group there if we want. It doesn't matter. We have those two options. So we just don't want something that's going to necessarily come off under basic conditions. So did we say T-butyl last time? So that is what we could do. So the sort of first step would be couple these two together. So once we make these, well, let's just talk about how we make these, right? You know, that's pretty easy putting on the protecting group, especially when you start abbreviating it, right? So we would start with valine. Again, I'm just going to show it in the neutral form. Obviously, as we discussed, it could be glitterionic in nature. But again, the condition would simply be FMOC chloride. So that's how we would make valine. From this standpoint, it would be from ornithine. And as we discussed, I think where we left off last week was we were discussing how you can protect the sort of primary, well, I guess it's not technically a primary amine, but the amine next to a primary carbon in the presence of an amine next to a secondary carbon. So you could argue, based upon sterics, that you could likely protect this one over this one. So, based upon what Shia was bringing up in terms of sterics, we discussed there could be other things, but again, from this standpoint, just that's what it is. And then again, we want to, we would want to protect this as a T-butyl group. So again, either way that you want to go about this, right, those are a few ways that we do it. We could also imagine deprotonating and benzylating and things like that. And so again, when you talk about reactions like this, you know, questions about, you know, what do you get alkylation at some of the other points, that could be an issue as well. Perhaps the acid in this case protonates the amine so that those lone pairs aren't able to actually participate in the bonding event. Now again, with these two groups, what you would do here is the first step would be the coupling. And so what's the reagent that we use? We could just say BCC. And then the second step, right, once we couple them, then the second step would be what? Deprotection. And again, the reagent that we learned was that trifluoroacetic acid, right, TFA. Right? That's going to get us this group here, right? Now, from a base standpoint, over here, again, we could imagine using, again, because the piperidine, suppose we could probably do the base-mediated hydrolysis. But again, at this point, what we use over here to protect this, yeah, the question is, yeah, but it's kind of, yeah. All right, well, let's just stick with that theme. So we discussed how, I actually don't know if this second part would work, but again, the sort of idea here is the orthogonality. So we learned that Lithium hydroxide could demethylate that, or could hydrolyze that, right? So that would be a basic condition. Actually, not sure, but I bet you lithium hydroxide would take off the FMOC, so that would be fine with that as well. Base-mediated conditions here. So that's what we'll say is for this one, it would be first a DCC coupling. And in the second step, because we want to do hydrolysis over here, we'll just say lithium hydroxide. And again, even though it's not the standard conditions, because it is basic, we'll assume that that would also take off the FMOC group because we've discussed this sort of base-sensitive reagent. Yeah.
So it's not going to affect anything else.
So lithium hydroxide can certainly hydrolyze amides if you force it, but certainly an amide bond is stronger than a ester group. So if you have an ester, it's much easier to hydrolyze an ester than an amide. Amide bonds are very, very strong, or much stronger. Oh yeah, lithium aluminum hydride's again, I told you guys fire in the lab, right? Yeah, yeah. So again, you can definitely hydrolyze amide bonds using lithium hydroxide. It's the same idea, sodium hydroxide, lithium hydroxide, it's a hydroxide, depending upon what the counter ion is, you could do that as well. But again, it's similar to, you can get sodium borohydride to reduce an ester. You can do that. But you can get selectivity for a ketone or an aldehyde over the ester. And so it's the same idea here. Again, this is just paper chemistry. But again, the idea is that the amide is more stable than an ester. And so you can hydrolyze an ester in the presence of an amide in the same way that you can reduce an aldehyde or a ketone in the presence of an ester. Okay? So again, this would be the general synthesis of this. And again, it's just a matter of protecting groups and recognizing these coupling reactions. All right, so this is simply a tripeptide that we discussed synthesizing. Right? So everybody will get a question like this on the quiz. So you're all welcome. Okay, if you get it wrong, make sure you get sleep so you don't get it wrong. All right, so now, from the standard building out, again, we just decided to do it one way. There's multiple ways, so we could have gone from N to C, C to N. Again, it doesn't really matter which way you go, you just got to pick one and then continue to go out in that direction. I want to discuss very quickly sort of concept of, so two things I want to discuss here. All right, I won't get ahead of myself here, but let's say that we have, say for example, this is fairly classic, just a benzyl carboxylic acid. Let's assume that we have just simple amino acids, okay? And what we're going to do, right, is we're going to do our DCC coupling with a Bach group over here. This will be amino acid 2. Right, so what we're going to do is we're going to do a coupling. That's going to be the DCC reaction. And the second step is going to be removing the Bach group, so that's going to be TFA. Right, now we're going to get a dipeptide. That's two reactions, right? Now one of the nice things about TFA, again, is that it's basically quantitative. Usually, you get very high yields. That's one amide coupling. Okay, so it's two reactions of DCC coupling followed by TFA deprotection. Okay, now in solution phase, right, you're going to run probably the DCC coupling reaction. When you're done with that, you're probably going to have to run a column, right? Chromatography. You're going to be handling the material. You're probably going to start to lose product. And so, you know, a yield that, say, for example, you might expect, right, just based upon handling and so forth. If you're really good, maybe you get a yield in the 90s if the reaction went really well. In your guys' case, you might get 120% yield, right? That's obviously not real. More likely, what you'd probably get is something like a 70% yield or something like that. If you had it on a good day, right? You might get a 70% yield over this sequence. So let's pretend we get a 70% yield here. Right? Okay, 70%, that's fine. Okay. So now we want to do a second anticoupling, right? All right. Now put on another amide coupling reaction. Okay, and let's imagine that that's 70% yield as well over that system. Again, a decent yield. In this case, I'm just going to abbreviate the amino acids here. Okay, so now we've got a tripeptide, right? And so the first reaction, we got a 70% yield. The next reaction, we got a 70% yield. So what's our overall yield through these two reactions going to be? What? 49, so 0.7 times 0.7, right? So you're going to get a 49% yield. Now what if you don't want a tripeptide, but what if, say, for example, you want a 10-member sequence, right? We would effectively, or 11, to make the math a little bit easier, let's say we want to make an 11-member amino acid peptide. AA is just amino acid. I'm just trying to abbreviate just to say something, right? This is not counting potential other protecting groups and stuff on there. But let's say you did 10 of these reactions to make an 11 peptide sequence, right? The overall yield through those 10 steps would be what? 0.7 to the 10th. I don't know what the math is. So that's why I made sure that I had somebody that had a calculator. So 0.7. So 0.028. So basically a 3% yield. Okay. So that means that if you started with, whatever you started with, you basically have just making a 10-membered peptide, right? For 11, for 11 amino acids at a decent 70% yield each, right? That's not a huge peptide, right? You're going to be overall 3% yield overall. So again, you're putting on mass this whole time, so perhaps it doesn't feel that bad, but when you actually start to think about the moles of what's going on here, you're effectively throwing out 97% of what you have. So it's not the most efficient method. And again, a lot of the mass that's perhaps lost in a system like this, right, is actually lost through handling, right? You have to, say, for example, if you have to chromatograph, especially with the DCC and the urea that you're trying to get rid of, right, you're going to start to lose mass from the column and the handling and all these other things. And so you can see as we start to build and get bigger peptides, right, to get a decent amount of material, what you need, right, is you need to get much, much higher yields, right? So 70% yield led to, after just 10 peptides, led to 3% yield. What if we were able to get, say, for example, a 90% yield? What's 90%? To the 10th, yeah.
23, no, 23, 40.
So now we're talking about a 34% yield. Okay? What about at 95%? What's 0.95? What's 0.95?
0.5.
Basically 60%.
The other one should be like 35.
Okay, so Ooh, close, 34, 35. Okay, well, look, but you guys see the point, right? When you're at 70% yield, right, 3%, right? You can get up to, say, for example, 90%. Now we're getting to something, at least in terms of 10, that seems much more manageable. We can even get up to 95%. Now we're getting most of our material at this point, right? So in peptide couplings, when you're repeating this process, it's really important that you maximize your yields. And again, because a lot of that yield will come from things such as purification and so forth, as well as perhaps reactivity and byproducts that are formed, you need a much better way to get a lot of material. And so what you can do, and what's often done in this type of chemistry, to sort of get that level of percent yields, 95% yields or even higher, is to use a sort of solid support, right? So we're going to learn about polymers in a little bit. One of the polymers that you can make is polystyrene. So we'll learn a little bit more about this later on. But this is styrene. Okay, some of you guys may have heard of polystyrene. Polystyrene is effectively the polymerization process of styrene. So what you end up having is, whether it's going to be radical, I'll just do it acid-base, right? What ends up happening is, right, you generate a carbocation, say for example you react with the acid, right? Then what's going to happen is another equivalent will react. I'm just going to start breathing this is pH just to make my life and the chalk easier, right? And then I'm going to add another equivalent. And on and on and on, right? And what we're going to have, right, is a polymer, right, that's going to look something like this, right? Now, it's going to react with a proton on this side, and then generally what you're going to have over here is, say, for example, a phenyl group, which you can imagine with that last step, you're going to have a cation there, and so you can trap that cation with different stuff. So there would be something would cap it. If it's an aqueous solution, there might be an OH over there. But again, it doesn't really matter because the majority of the compound is going to be made up of these polystyrene components. And we'll learn a little bit more about this later on. Now, if you do this polystyrene polymerization process, you can do it as a copolymer in the presence of things like, say for example, benzyl alcohol polystyrene, or something like this, or say for example, chloride, right? And now what you have is you have a polymer that's composed of mostly these things, but what you have periodically is something like this. Again, it's not going to be the pure version of this, as I'm sort of suggesting, but so it'll be a mixture of the two. What you'll have is a chloride like this, right, on a polystyrene bead. So now you got a bead that's polystyrene that's effectively coated with these chloromethyl groups, right? From there, if you have something like, say, for example, a carboxylic acid, you can functionalize this, okay? And actually put it on, this is often what we'll do, is put it on a bead. So you have a bead that's going to be coated with all these different things. And so this is formally called Merrifield resin. Nobel Prize was awarded for it. And what it allows, right, is instead of all those things that we discussed previously, right, if you want to do a reaction like this, right, one of the nice things is that you can run this with ECC. And this might not matter at this point, but on the first peptide, which you can imagine benefits later on down the road, is that you can use a whole ton of this material, right? You can maximize how much of this you want because it's really easy just to wash it away once you're done. So what'll happen is you'll link this, right? And then what you can do follow the TF80 protection and everything else, right, is you have the bead, right? It's solid. It's not going into any solution. So you can wash it. You can wash away all the urea that's generated that can be difficult to get rid of. You can wash away any excess peptides. So you can use a whole bunch of this to make sure that every single, or as close to every single molecule of this reacts. You can push it, right? And that would have even more benefits as you're getting to longer and longer and longer peptides. And so what this can formally allow you to do is get up into those higher 95, even above % yields, right? Because you're not losing that mass through all that handling. All of the molecule stays on the bead. You can do the chemistry and keep all those beads. This has been automated now. You can actually do automated versions of these where the beads will basically get washed by some type of automated system and take it through this entire sequence. So there are literally peptide synthesizers now that you can get where you'll have like different amino acids, right, as compartments, and you just literally type in the amino acid sequence that you want, and it'll start building up it for you. It'll just go on its own. And again, there's things like microwave-assisted reactions that'll actually accelerate this even faster. And so this is a sort of general idea in terms of getting up to these, say, for example, higher molecular mass amino acids. Now, what we were talking about earlier was amino acids of about 10 or 20, right? And so this, again, huge benefits. Nobel Prize was awarded for solid-phase peptide synthesis, and certainly this allowed manageable amounts of peptides. Like we showed you, if you can get a 95% yield, right, you might get 60% yield of a 10 peptide compound. But the issue is that you start getting longer. There's two things that can take place. And the first is just pure math, right? If you, back to the calculator, right, if you had a 95% yield, and let's say you wanted to make, does anybody know roughly what the average size of a peptide or a protein is? How many amino acids? About 300 or so, 300 to 400. So let's say 300. If we wanted to make let's say we wanted to make an actual enzyme using this technique, that would be 95.95 to the 300th. Okay, even with these types of yields.
0.0000000.
So 0.0020, because it would be 00, or no? Yeah, because it would start here, because we're in percentages. So 1, 2, 3, 4, 5. Okay, I think we're good. So you can see, right, that if you want to use this type of approach and actually make enzymes, right, even with these super high yields, you wouldn't be able to do it. Or you would basically be throwing away 99.99998% of your material, right? And so it's just not feasible to synthesize things like enzymes. And certainly there's enzymes that are even bigger. There's enzymes that are as large as 1,000 amino acids or even larger than that. So again, if you want to have this level of control and make enzymes using solid-phase peptide synthesis, you know, it's not going to be feasible using it through this type of approach. Okay. Now, certainly you guys will learn about things like PCR and biochemistry, and there are certainly other techniques to sort of do this. But I think that one of the things that organic chemistry has that, say, for example, other types of approaches doesn't necessarily have is a level of control in terms of constructing molecules, right? If you can make a molecule and fine-tune one amino acid at a time, that gives you a certain amount of control that perhaps you might not have using a lot of biochemical techniques that you may learn next semester. Specifically, let's say, for example, you had an unnatural amino acid that you wanted to incorporate into this. Certainly people have come up with biological tools for that as well, but again, you might then have to come up with that tool to be able to insert that unnatural amino acid. So if there's one that, say, for example, you don't have that tool and you just came up with, you could either spend all the time developing some codon to sort of incorporate that one in, or you could try to do the peptide synthesis, right? But as we just described, that's not going to be quite feasible. Until recently, and this is one of the reasons I want to talk to you guys about this, we Tom Muir is coming out in a few weeks. The person that developed this idea that I'm going to talk to you about today is a guy, Stephen Kent. And Tom Muir was, I believe, a postdoc in his lab at the time. It was basically one of the co-authors on the seminal paper on this idea of native chemical ligation. Okay, so if you wanted to synthesize again, let's go back to that 95% yield, right? I'm going to be throwing numbers out again, so have that there, okay? So again, what we discussed previously is if you had 95% yield and try to make, let's just make the math a little bit easier now. Let's make a smaller enzyme. Let's say 100, because I think I might have this number written down. So, oh, actually I have it for 90. So can you put 0.95 to the 100?
Yeah, 0.0059.
Or point would be that, 0.5. Okay. So again, a fairly low yield. Again, we're just going to do this to sort of compare the numbers and to sort of show you benefits. Again, this is just if it's 100. Okay, so if we have 100 of these, we're going to get about 0.5% yield, right? However, we know that 95, if we did it 95 to the 10th, that's going to be a really high yield, right? What do we say, 60%, right? What we had from previously? That's 60%, right? So what if instead of doing 10 reactions, what if instead of a linear sequence where we did it 100 times, what if instead we made 10 subunits, right? 10 sets of 10, right? If this is a 100 amino acid unit, we did 10, 10, 10, 10, 10, each of which we would be able to get about a 60% yield. And then we would couple those together, right? Thus, what our yield would effectively be, in essence, again, this would just be a shorthand, would not necessarily be 0.95 to the 100th, but would be 0.95 to the 10th to the 10th, which would basically be 0.95 to the 20th. And if we think about that, just so that we can get a comparison in terms of yields,
Would be
35% yield. And again, this is only talking about 100 mer peptide. So again, comparing these two, when we start thinking about the efficiency of that process, right, you can clearly see that's roughly 70 times as much material, right? And certainly that's going to become, as we saw earlier with 300, that's going to become even more pronounced. So this idea of, this would sort of be what we would call linear, right? This method would be one that we would call sort of divergent, I guess. Okay? But there's one problem, and that's that when you have big, that seems fairly simple, right? It's just algebra, right? But the issue often associated with peptides is that once you start getting a couple issues. Once you start getting these much larger peptides, right, you start to get three-dimensional folding and things like that. So a lot of those yields that we talked about, those 90%, 95% yields, because of the fact that you start getting these secondary structures, they start making the coupling yields go even lower. Yields start dropping, in part because of the secondary structure, and it just doesn't end up working out as well. And so in order for this sort of divergent approach to take place, what needed to happen is new synthetic method development that would allow you to couple two units together with that level of efficiency perhaps that we were talking about earlier, perhaps even higher, quantitative coupling of these two fragments. And the method that was developed, again, with at least part in due to this year's Friedman lecture, again, this idea of native chemical ligation. So the idea behind this reaction is that if you have a peptide, we'll say peptide 1, peptide 2, so the idea is if we took these two fragments and we tried to couple them together, we get very low yields, again, because of those factors that I showed you before. not very good, we'll just say. Okay? But what was developed that allowed this to actually work really well is this idea here. So if you have a peptide, and what if you have on the ends, instead of the carboxylic acid on the one hand, if you have this thioester. So instead of the OH, you have this SR. Usually it's like a phenyl or something like that. Okay? And then on the other end, what you have right? So first things, if you suddenly had this thioester, right, now this is a little bit more active. You might not need the DCC, because that's the other thing, right, is that you might need DCC in these types of situations as well. But again, the other issue is if you have, say, for example, ornithine side chains, right, or amine, lysine, right, if you have an amine hanging off, or something else that could also react with this, that might not be good, right? So you need an element of selectivity. And what this reaction is, take cysteine. Okay, these will actually react together really, really well and really cleanly, with preference for this binding event, okay? So what is special about this event taking place? Well, there's two things that are taking place here. First of all, sulfur is, as we sort of learned, is a fairly good nucleophile. In fact, oftentimes under physiological pH, that can be deprotonated and it can be the negatively charged species, so that's kind of nice about it. But the other thing that it does is it gives you a little bit of an extension, right? We discussed that nitrogen, right? And one of the big issues with that nitrogen is the same thing we were talking about before, right? It's a primary amine, right? But it's next to that secondary amine, so it's perhaps not going to be all that reactive. But this thiol is fairly reactive. And what can happen in this case is that the first thing that happens is that the thiol actually makes a new thioester bond. So that's the first step in this reaction. You effectively exchange. Again, this is well known. Thioesters can exchange very rapidly back and forth between one another. Okay? And so this is reversible. So we'll just say P1 now, make it smaller. Okay, so we make a new thioester bond. That's what this is called, a thioester. Okay? What happens with this new thioester bond is that now, again, it's reversible, but now that it's here, you have this 5-membered transition state, or sorry, transition state, 5-membered ring that you can, in essence, form. Okay? And then what happens is once you get to this point, you leave, and now you get a native bond fairly cleanly and quite selectively. So this is again called native chemical ligation. Again, it works very, very well near quantitative yields, and all you have to do is you have to pick the right amino acid. You have to pick, you just have to find where you have the appropriate amino acid, and then you can, in fact, undergo this coupling process. And so oftentimes you can take two free fragments, right? It doesn't matter if there's lysines on there. It doesn't matter if there's other reactive components on there because otherwise there's nucleophiles. These will find each other at those two bonds, and they will make that bond in that position. Okay? So again, this is a fairly simple mechanism. I'd like you to know it, but more importantly, I think it's worth it for you guys to sort of see that this is something that's a lot of your textbook. I think one of the issues, especially now when we're getting into more biological-based stuff, a lot of the textbook is sort of archaic, right? It was made many, many years ago. And so one of the things that I'd like to try to do here, and what I kind of want to do with you guys is show this is something that happened, well, show my age here. I guess like when I was sitting where you guys were, so this was like in the mid-90s when this was sort of developed. So this tool of sort of ligation, native chemical ligation, allows the synthesis of huge peptides. And so again, when I was an undergrad or so, this type of technique was just coming out. And so people didn't have the ability to do these. And one of the things that this is now allowed, again, is a lot more control at that biological level, right? If you want to be able to synthesize enzymes, if you want to be able to make modifications to enzymes in a more controlled way, this could potentially be a very good route. So anyways, I think it's pretty cool. And what's still happening today, right, is this sort of question, well, you know, you always have to deal with the situation where you have the appropriate amino acid, right? But one of the things that people are now trying to do is do things like, can you have alternative sort of mimics that do similar types of things for, say, for example, other amino acids, such that you don't have to sort of base your chemistry on the sequence, and at least perhaps maximize those types of yields. So anyway, so that's native chemical ligation. And again, if you're sort of more interested, and I posted a link to other types that people have developed subsequently. But again, this came out in the mid-90s. Okay. Okay. All right, so I don't have. I have the textbook here. So I guess with that, this is kind of really all that I wanted to talk about for peptides. Again, there's things like Edmond degradation that you can look in the book and stuff. But again, I feel like back to things that are more archaic. That's not how people usually sequence amino acids anymore. It's pretty much all automated, huh? Because mass spec, yeah. So. Excuse me. No, geez, excuse me, thank you. Again, I don't want to go into the details behind it, but I could sort of give you people have just come up with much better techniques to figure out what peptide sequences are. Sometimes they can, again, I don't understand all the details about it, but sometimes what you can do is you can effectively find out what the peptide or the protein sequences based upon like the oligonucleotide sequence, for example. So you can that could be one option. The other thing is something called tandem mass spectroscopy. So there's techniques that effectively will get a mass spec and then get a subsequent mass spec from the mass specs and things like that. And somehow, again, I don't understand the math behind it, but there's like algorithms that are used that can effectively be used because each, if you think about it, each amino acid has a specific mass characteristic to it, right? And so if you say, for example, have a tripeptide sequence, even within a greater, say, 301, there might be that 3-component sequence, but you don't know which order it's in, for example. And so when you do this tandem mass spec, you get all these different collections of all these different fragments, and then the computers somehow piece it all together. It's kind of like, well, it's math, but it's computers. It's computers. But so techniques like that effectively make Edmond degradation. Because what Edmond degradation is, again, it's classic. It works for small peptides because what you do is you treat them to that, and you just chop it off at the end terminal one at a time. I decided I'm not going to teach it this year, just because. Yeah. So okay, so we got half hour. What do you guys want to do? So you guys want to do, so one of the things, you know what I'll do for starters, because somebody in my office last Monday, we were discussing this sort of idea of Fisher projections to sort of chairs, right? And I think one of the challenges that people often have, right, is that perhaps they've learned some rule, and then that rule gets confused, and they end up like drawing the enantiomer or something like that, right? So I think that maybe what I'll do for the next 10 minutes, 15 minutes is we'll discuss that, because that's going to be on the quiz, right? So at least we'll sort of prepare for it. At least I'll go through it a little bit more detail, get you guys thinking about it. And then I'll have another 15 minutes if you guys want to do something else. So think about what you might want me to do the last 15 minutes. So again, I told you guys that there's going to be a question, something of this variety, right? Where you'll have sugar, I have no idea what the sugar is, but you're going to want this sugar, and what we want to do is just put it, because again, Fisher projections are kind of like, I don't know, they don't really tell me that much. They're used a lot in sugar chemistry, but I think getting back to the sort of practice of redrawing molecules, getting in the handle of seeing them in 3 dimensions, again, you're all going to get a question on the quiz that's going to ask the basic question of, can you convert this into a chair conformation? Again, as we've discussed, there's perhaps 4 possible right chair conformations that you can draw. There's the 2 chair flips, and from within them, the anomeric carbon being in either the axial or equatorial position. And any one of those 4 will be fine. I just want you guys to put it into a structure that's sort of a little bit more descriptive than a Fisher projection. So that's kind of why I want you guys to do this. Okay? So again, the tricks, I don't want to call them tricks, but let's say the strategy to sort of go about this, I think again, Fisher projection at the very beginning, you have to know what the Fisher projection means. So unfortunately, you have no choice but to sort of memorize what bonds are going in which positions, and this is again why this sort of bow tie rule comes into play, right? If we have this molecule, we've got our bow ties, right? So this is the first thing that we can sort of think about is, what is the stereochemistry to this? And again, everything on the horizontal axis is going to be coming towards you, right? Which means that everything in the vertical, right, is curving in on itself. Right? And basically what it means is that everything within this molecule, and even within each of these bonds, this molecule is literally coming together like a claw, right? Each one of these bonds is coming together like a claw, okay? So, if we want to make a hemiacetal through that claw, which atom do we need down here to make that 6-membered ring? This OH, right? So the first thing that you want to do, and from a strategy standpoint, is to sort of recognize that it's bending down like this, but you need that OH there, right? So the first thing that you kind of want to do is rotate around this bond to put the OH here. What you don't want to do is simply swap the OH with something else, right? That's going to change the stereo center, right? You need to rotate all around. So the OH is going to move here, the CH2 OH has to go here, and this H has to go here. You hold one steady. It's similar as if you're rotating around, say for example, a Newman projection, for example, right? And so again, first thing you should do is redraw it. Okay, and again, this OH rotates down here, and this OH rotates down here. This guy is going to be over here, and this H is going to be over here, okay? And the important reason to do this, and what's helpful about doing this, right, is that what you recognize then is when this does curl up on itself, when it does start to form that claw, right, that's how the ring is being made. And when that ring is being made, right? Everything that's on this side is going to be on one side of the ring. And everything that's on this side is going to be on the other side of the ring. Now the trick is that once you try to draw this, you can put it into a Hayward projection if you want. And you can go from the Hayward to the claw, or sorry, for the claw. My daughter just became a big fan of Inspector Gadget. There's a guy called the Claw. She calls it, yeah. Sorry, I shouldn't be doing these retro synthesis arrows. All right, enough of the Inspector Gadget theme song. All right. So again, how you go from here to the product, I think that in general, I like to sort of go directly to the chair, but I understand that sometimes going to the Hayward projection can be helpful for you people, or you guys. So I think that going... Didn't mean it that way. But again, I think I'll do it with the thing here, right? But if you sort of look at this molecule, you're pinching it, right? And this is sort of how I was trying to explain it upstairs in my office, and so I'll try to do it the same thing here. Depending upon which hand you use, so whether it's your left or right hand, right? If you think about that sort of pinching together as a claw, right? And then what you're going to do is you sort of want to rotate it on its side, right? So when you're forming that ring, and then you're turning it this side, to get to the Hayward, so again, this and this are going to form a bond, and then you're going to turn it this way. Okay? 2 questions. You can go the other way, but that hurts my arm. I'm just going to go this way because there'll be a different molecule that you generate. If you go this way, one part will be on the top. If you go the other way, the other part will be on the top. I could have gone this way with my right hand, but I just have my left hand. Okay? Now when I twist it this way, where is the hemiacetal going to be? Where is the anomeric carbon going to be? Is it going to be here or is it going to be here? Well, it doesn't matter if it's up or... Not if you're twisting it this way. It's going to be on the top. Okay, hold on. And a lot of people said down, so that means that this isn't helping. So when I form this bond, I wish there was some intermediate that I could draw. Draw like a straight horizontal line. Yeah, this is, I think, the part in the course where I just need to have somebody else show you guys. Oh, that's a good idea.
Yeah, so this side will have the C-H-O. This side will have the O.
Yeah, that's a nice intermediate.
1, 2, 3, 4.
Right.
That side of the O. This stage is O.
Perfect.
And this is C.
Love it. You get an A. All right, this is great. That's so simple. See, this is the type of tricks that help, right? Because you're just looking at it in a different perspective, right? You're just looking at a slightly different perspective. And now when it goes around, right, you guys can hopefully see, now is it a little bit easier to see that when it does that claw, the OH is in the back, right? Because what I have here is, this is in the front, this is in the back, right? That's the Hayward projection, okay? But the beautiful thing is that now as Shio is drawn, right, we know where everything else is, right? So that guy's going to be on that side. Again, they're going to be coming towards us. Okay, and now I'm going to erase this guy here, but that's great. Okay, and this is, I think there's an important lesson here, and that's that, well, 2 important lessons. Sometimes it's much easier for you guys to explain some of these things than me, because I've been doing this for 10 to 15 years. But the other thing is that it's also really valuable to just redraw in a different perspective, and for some reason, saw that or learned it somewhere, but it actually ended up working really well because you did put it into the dimension of the molecule. And then at this point, again, it doesn't matter where this OH is, it can be up or down, but then I'm sure that you guys could all fairly quickly turn it into the chair if the question was to turn it into the chair. Right, so if this is the OH, this one doesn't really matter. We'll just put a squiggle OH. Again, we can have axial or equatorial. This carbon here is going to be up, right? It's going to be up axial or up equatorial? Equatorial, right? This one's going to be down equatorial. Right? This one's going to be up equatorial. This one's going to be down equatorial. So this is all equatorial. And again, you could draw it all equatorial. If you drew the other chair, that's fine as well. Because, again, within sugars, the fact that one chair might be a major chair versus the other is a lot more difficult to predict, in part because of, again, if you showed all the axials, right, you'd have all that hydrogen bonding, which could also help stabilize it. So, great. Okay? So again, practice this. I'd like you to see it again. I like the turning it on its side. You were trying to tell me that before. I should have just brought you up here last time because I didn't quite understand what you were saying. But it's brilliant, right? You're just putting it on its side, and maybe it's a little bit easier to see. So again, depends upon where you are. Just make sure that you get it right. If you're not sure, because one of the challenges I think, right, in organic chemistry, just more generally, right, is sometimes you don't really know. Sometimes it's difficult to know whether your answer is right. And again, my issue is that sometimes even when you guys see the answers, you misinterpret it, which is one of the reasons why I don't post my answers. I don't want you guys talking to us, but in this case, something like this, you can certainly get a model set to help sort of at least confirm if you're getting the right answer or not. So you can sort of use that model to sort of help you out. Okay. All right. Anything you guys want me to know? You had your hand up. Oh, who? Oh! Mm-hmm. Yeah, absolutely, yes. It's only anomeric carbon. So right, so the anomeric effect is basically, and you can see this, it's actually when you see the geometry of these molecules. So again, anomeric effect is something that I think is certainly interesting to show. Specifically, if, say, for example, you had, so here's the question that I had in the quiz, on one of the quizzes. Okay, so here are two diastereomers, right, that equilibrate rapidly through a mechanism that you guys should all be able to do, right? This is a mechanism, the interconversion between these two, you can use an H+ if it helps get through the process, right? But the mechanism through this process is one that you guys should be able to know. If you have confusion, just look back to the Carbonyl chapter or ask it some other time. Chapter 16. The question in terms of this chapter, in terms of the anomeric effect, and this is one of the questions that I asked on a quiz last year, was which way does this equilibrium lie? And more importantly, why? Because it turns out, depending upon which answer you said, I gave the answers to either one, but you had to explain it well. And so there's two possible answers that you can give, one of which is the anomeric effect, and one of which is, so there's kind of two parts. The first is convert this to a chair, though. Convert each of these to a chair, right? And the reason, perhaps, that I have a T2 group there, right, is probably what? To sort of lock it into a specific position, right? Because that T2 group has to be equatorial. A T2 group will never be axial. And this is where some of the confusion came in when I explained the anomeric effect. People assumed, I mean, this is where your question's coming from, people assumed that what I was saying, or misinterpreting what I was saying, to mean that if you have an anomeric carbon, then suddenly everything's going to go axial. It's like, no, that's not what it means. Specifically, what we're talking about is only this position and only when it's a hemiacetal or acetal. Okay? So you have to have sort of heteroatoms there. Okay? Now, we're going to draw this as the chair. The question becomes, the point that I'm asking is that carbon-oxygen bond based upon this stereocenter with this here, is that going up or is it going, sorry, is it axial or is it equatorial? It's going to be equatorial, right? So this is coming at you, this is going to be going away from you, so this is equatorial. And likewise over here, okay. Now, your assumption, right, before I talk to you about the anomeric effect, right, would be this, right? You would say the oxygen is equatorial. Because the oxygen is equatorial, that's more stable because I learned that last semester and I apparently wasn't paying attention during the anomeric effect discussion and my book didn't say anything about it. And so if a student had said equatorial because, you know, this one, and they drew the chair and said because this has got to be equatorial and this is also equatorial. So if they said that, I gave them credit, but the answer that I was looking for was this one here for the anomeric effect. Now, to go into a little bit more depth to help explain why this is the carbon, right? Because that's what it comes down to is if you don't understand the reasons behind the anomeric effect or what the anomeric effect argument is, then that's where a lot of that confusion can come in terms of, oh, well, it can be other positions. It's only this, and this is the anomeric bond. So it's the anomeric effect is basically the hemiacetal or acetal carbon, right? This is the anomeric carbon. It's the carbon within this ring system that is bonded to both an oxygen and basically two oxygens, so hemiacetal or acetal. Right? And what leads to this preference, at least as it's believed, and there's certainly data that supports this, specifically this carbon-oxygen bond is much longer, this carbon-oxygen bond is much longer than your typical carbon-oxygen bond. Okay, I don't have the specific numbers, but this is a much longer bond. And what that suggests is an elongation of this. And this provides preference for this molecule. And the thought is that very similar to an elimination reaction, right? If we go back to discussing elimination, right? Anti-periplanar, right? The idea behind an elimination reaction, the reason why you sort of need this anti-periplanar nature to this, is the electrons that are in this carbon-hydrogen bond that are eventually going to make that double bond are lined up in very close proximity to the sigma star. Analogous to that, this axial lone pair is lined up very close in the same way that these lone pairs are lined up with this. This lone pair, this axial lone pair, is lined up. This is basically anti-periplanar to the hydroxyl, meaning that it back bonds into that sigma star there, thus elongating that system. And again, electrons, like I tell you guys, oftentimes when I think about electrons, I think of them as being claustrophobic. Right? If they can be localized somewhere else, that will be favorable. This is why resonance forms are so beneficial, right, in terms of stabilizing different compounds, in addition to sharing charges and stuff like that. But again, if a molecule, say it's a conjugated diene, right, is so stable because you're allowing the electrons to flow throughout a longer system. That's effectively what's happening here. These lone pairs are doting into here towards an extreme resonance form. It would be something like this. Right? So that's obviously a broken bond. That's not really what's going on there, but that's sort of an extreme resonance form that illustrates this sort of binding ability. So again, I just think it's something interesting about sugars. I think it's something worth teaching. Certainly it's not in your book, but I think when we learn all about axial equatorial, we've learned about why antiperiplanar bonds are the way that they are, right, in terms of needing to have this antiperiplanar in order to undergo the elimination. I felt that it was a nice sort of combination of all those things to sort of learn a new concept, which is the anomeric effect. And now you can argue why the anomeric effect is what it is. Like, is it because of this lone pair? Well, I think the fact that this bond is longer is a pretty good indication of something like that going on. But again, it is favored oftentimes, and again, I showed you guys an example of this even in our own chemistry, where that was the case. Yes?
But it's simply just two answers, right? Like,
I didn't want two
you can't
answers.
say-
I didn't want two answers.
Right, like you can't pick which one's gonna win, basically, right?
So I think, as is usually almost always is my case, the right answer is secondary to the explanation, right? Like, what I'm looking for first and foremost is that you provide an answer that is dependent upon rational chemistry, right? That's built upon chemistry. So if you get the wrong answer, but you have a very logical reasoning for that answer, I will be very generous, possibly even full credit. And in this case, that was what I did, was that if people said this because it was in the equatorial position, I just gave it to them, yeah.
Would the bond have anything to do like character in reality? Like,
This oxygen here?
that oxygen that carbon bond.
Yeah, would this be like a double bond? I actually don't know. I mean, that would be an interesting question. I don't know. I don't know. I mean, I don't know. You imagine it might, right? In the same way that an amide might. So there may be some, in addition to the bond elongation, I don't know, but you might imagine that in addition to the bond elongation, there might be twists to the bond angles and stuff, which might imply that it does have a little bit more S character to it, as you're sort of suggesting. So I don't know. It would be, I kind of want to go look that up now if I had the time. So, all right. Any other questions? Yeah. No. Wouldn't this? Oh, this is not really happening. I was just trying to sort of draw a very, very, very extreme resonance form in the same way that you would draw perhaps an extreme resonance form with, say, for example, or even a ketone, right? Like how we discussed that resonance form as being like how it reacts. So, but the bond is longer, but it's still a bond. It's not dissociated. I was just sort of drawing that to sort of help further illustrate this point. So, yeah, this is not, yeah, so, yeah, this isn't suddenly behaving as a hydroxide, if that's what you're sort of wondering. Yeah. Any other questions? Okay, well, if there's no other questions, I guess I'll let you guys out a little bit early. So. All right?
Yeah.